Hallo alle miteinander. Today we are going to take a look at how to find the area of a regular polygon. So let's do a quick review. We've talked about regular polygons, but it's been a while. So let's just do a review of the definition of a regular polygon. It's going to be a polygon in which all the sides and all the interior angles are congruent. Oops, let me try respelling that. Congruent. There we go. So in other words, a regular polygon is both equilateral and equiangular. So there are a number of ways you could find the area of a shape like this. This happens to be an octagon. So you could break it into a number of different shapes. You could draw some segments that would break it into maybe a couple trapezoids and a rectangle. You could break it into a number of different triangles. But thankfully, since it's a regular octagon, since we're going to say that all these sides and angles are congruent, we are going to learn a formula that's actually rather easy to use that will help us find the area of this regular octagon. And the nice thing about this formula we're going to use, it works for any regular polygon. Same formula for a regular octagon or a regular hexagon or a regular pentagon or a regular triangle. They would all use the same formula. So first of all, we need a few definitions of parts of a regular polygon. Let's imagine that we have a regular polygon that's inscribed in a circle. So I'm going to make an attempt at kind of inscribing this. It's not going to be perfect by any means, but we're going to get an idea. Remember, if we inscribe a polygon in a circle, what that means is that all the corners of the polygon, oh, this is terrible, all the corners of the polygon are going to be on the circle. So in other words, all these corners, all these vertices of this octagon will be just touching this crudely drawn circle that I'm adding to the notes right there. So every corner is just touching this circle, and that means that polygon is inscribed in the circle. Then some terms that we need to know about that polygon. First of all, that polygon, you can see that point I that's kind of in the middle of that octagon. Well, that is actually going to be called the center of the polygon. It's the same as the center of the circle that is circumscribed around the polygon, or that the polygon is inscribed within. Next, we need to know a term called the radius of the polygon, and that would be the distance from the center out to a vertex. And it kind of makes sense that we would call it the radius of the polygon because it would also be the radius of this circle that we've drawn around the polygon. So in other words, if I connect I to D there, that segment would be a radius of this octagon. A central angle of the polygon is going to be the angle formed by two radii that are drawn to consecutive vertices. So I've drawn one radius right there from I to D. If I drew another one from I to C, that would be, let me try to draw that a little bit better. From I to C would be another radius, and so that angle that I just created there, that would be a central angle. This right here would be a central angle of this polygon. You can usually figure out the measure of a central angle of a regular polygon because you can just take how many sides it has and divide 360 by that number. Since if we went around and kind of divided this octagon into 8 kind of pie slices, if you will, each one of those pie slices would have one of those central angles, and they would all be the same. So we could take, for instance, from this octagon, we could take 360 and divide it by 8, and that would be the measure of one of these central angles. And that would end up being 45 degrees. So this angle right here would be 45 degrees. And lastly, a new term, one that you probably have not heard before, it's called the apothem. The apothem of a polygon is the distance from the center to a side. So in other words, if I go from the center I and I go over here to segment DC, which is a side. Now remember, if we measure the distance from a point to a segment, we're going to measure along a perpendicular segment. So that apothem will always be perpendicular to the sides. That's going to be this distance from I, we'll call this point right here, we'll call it M. That will be the apothem. And the apothem of a regular polygon will always bisect the side that it's going to. So that would mean that DM and MC would be congruent. And you'll need to remember that for some example problems that I'm about to do down here. So those are some terms that you're going to need to know, specifically this one right here, this apothem, because you have to use that in Theorem 11-6, which is that formula for regular polygons that I was telling you about. So the area of a regular polygon is equal to half the product of the apothem and the perimeter of the polygon. So, of course, we usually like to see these written out using, a shortened version of it. So what you can think of is area equals half of AP, where you just need to remember that A stands for apothem and the P stands for perimeter. And remember, when you find the perimeter, you're adding all the side lengths of that shape up, or since we're going to be looking at regular polygons, you could take one of the side lengths and multiply it by however many sides there are in your polygon. So for instance, if I knew in my octagon right here, if I knew that, let's say, AB had a length of 5, then the perimeter of that would be 5 times 8, or 40, since there are 8 identical sides that are all 5 units long. So keep that in mind when you're doing perimeter. Let's look at a couple examples. I'll do the first 3 on this video, and then we'll probably take a look at the last example in class. So here we have, they're each regular polygons. So this looks like a square, and we can assume that it is a square because a square is a regular polygon. It's a regular quadrilateral. It's a quadrilateral where all the sides are congruent and all the angles are congruent. So what we're going to do is we're going to use this new formula, 1/2 AP, to find the area of this square. And you can see right here we've got this distance, which of course by the definitions that we just learned up here, that would technically be the radius of this square. That's given as 5√2. Now, we need to keep in mind that this little triangle that is created when I drew that radius from the center of the square out to the vertex, that's going to be a 45, 45, 90 triangle. Each of these angles right here, those will both be 45 degrees. And if we're going to use this formula, we need to know this distance because that is our apothem right there. And we're also going to need to know this distance because that's going to be half of one of the sides. And we'll need to know a side length so we can figure out the perimeter. Thankfully for us, we remember that in a 45, 45, 90, the hypotenuse will be the leg times the square root of 2. And this 5√2 is obviously the hypotenuse of this 45, 45, 90. So now we have 5√2 equals the leg, which is going to be the apothem, times the square root of 2. And you should be able to look at this and realize that if 5√2 equals a√2, then 5 and a have to be equal to each other. So our apothem would be 5. Since this is 45, 45, 90, this other leg is going to be the same as this one, so that's a 5 right there. And like I told you over here, this apothem is going to bisect this side of that square, so this part of it will be 5 there. So one side of that square would have a length of 10, meaning that the perimeter of the square would be 10 times 4, or 40. So now we have our two values that we're going to use in our formula right here. We're going to take half of 5 times 40. In other words, we're going to take half of 200, since 5 times 40 is 200, and that's going to give us an answer of 100. Now for example B, we have a regular triangle, also known as an equilateral triangle. In an equilateral triangle, we recognize that each angle at each vertex is going to be 60 degrees. This radius is going to bisect that angle. So this is going to be a 30-degree angle, which means that this is going to be a 60-degree angle. And this little triangle right here is a 30, 60, 90 triangle. We need to know this distance, and we also need to know this so that we can figure out the side. So the apothem right here is going to be the short side of my 30, 60, 90. So I know that the hypotenuse is 2 times the short. 8 is the hypotenuse. The apothem is my short, so 8 equals 2a. If I divide both of those by 2, I get that the apothem will be 4 units. Now that would mean that this is going to be my long side of my 30, 60, 90. So it's going to be the short times the square root of 3. So that's going to be 4 square root 3. If this part of it is 4 square root 3, and remember the apothem bisects each side, that would mean that the total side length is going to be 2 times 4 square root 3, or 8 square root 3. And if one side of this triangle is 8 square root 3, then the perimeter will be 3 times 8 square root 3, which is 24 square root 3. Now you could do this as a decimal if you wanted, but I'm going to leave it in radical form. So now I know my apothem right here, and I know my perimeter right here. So when I use this 1/2 a times p, I'm going to be looking at 1/2 of 4 times 24 square root 3. Half of 4 is 2, so now I'll be doing 2 times 24 square root 3, and that's going to give me 48 square root 3. Again, you could do that as a decimal if you wanted, but I'm just going to leave it in radical form. Lastly, we have right here a regular hexagon. It's got 6 sides. So how are we going to figure this one out? Well, we would know that the central angle of a hexagon, if I drew another radius right here, going over to this vertex, this angle right here would be 360 divided by 6, or 60 degrees. And it's going to be bisected by the apothem that's drawn right here. So I'm looking at another 30, 60, 90 triangle. In this case, the apothem will actually be the long leg, and this right here will be the short leg. And since the hypotenuse is 8, just like it was up here, I should know these two distances. It's going to be the same things, the same numbers that I found right here for long leg and short leg. Only now, this is going to be my short leg, so that'll be 4. This will be 4 square root 3. Let me clean that up. That's a little bit sloppy. 4 square root 3. So one side of this is going to be 4 plus 4, which is 8. So one side of this hexagon has a length of 8. The apothem is 4 square root 3. So the perimeter would be 6 times 8, which is 48. And again, the apothem was 4 square root 3. So the area will be half of the apothem times the perimeter, which will be half of 4 square root 3 times 48. Half of 4 square root 3 is 2 square root 3. So now we're looking at 2 square root 3 times 48. And 2 square root 3 times 48, we can just multiply the 2 times the 48 and then tack on the square root 3. So that's going to be 96 square root 3. Okay, folks, in class we'll be taking a look at the area of a regular pentagon with a radius of 5. So if you want, you can try first drawing out that picture, and then in class we will take a look at how we can calculate the area of that. All right, so I will see you then, and good luck with this section.